Hello, I'm Adam Chapala. I'm on the faculty in computer science at MIT, and I'm going to be talking about how formal methods can help us avoid some of the surprising security problems that have popped up in processors recently. So we all know Meltdown and Spectre made a big impact in the computing world, where they involved surprising ways that optimizations we were all used to in our processors led to leaking of secrets through timing behavior of systems. So what can we do about that? Well, here's some brainstorming ideas. We could all promise each other we're going to think harder about the implementations that we build and stare at them and give them to other people to stare at, but this probably isn't actually a scalable or effective solution. We could just stop using the optimizations that have become standard and that in some sense were responsible for the security problems that emerged recently. This probably isn't going to be a hit with customers either. Or we could apply formal verification to provide very principled guarantees that the designs that we implement avoid whole classes of security problems. And that's what I want to talk about now. So a quick review of a Spectre-style vulnerability in a processor. We have the processor, and it includes a branch predictor that makes guesses about which way jumps are going to go. And the processor is accessing a cache memory. We have some pictures here of where individual slots of the cache are being used to replicate objects from memory. The branch predictor sometimes makes a bad guess about the way a jump should go. We start down some path of executing code. And as we're going, we're actually touching the cache, maybe adding new entries into it, evicting existing entries. Eventually, we realize, oops, that there was a faulty prediction, and we need to roll back everything that we just did. Except it's not quite everything. Usually, the cache side effects remain in place even when we roll back a bad branch of speculation. So we eventually get our correct prediction, restart the process, cause some different side effects touching the cache. But we can also, through timing, observe the fact that we started in a different cache than we would have had if we'd made the right prediction in the first place. And so your secrets can be revealed when they have somehow influenced this trace of memory addresses that are being touched. So how could we convince ourselves that a processor does not leak information in this way? Well, a thought experiment would be, whenever we start down a speculative branch, let's checkpoint all the relevant state of the processor. And then whenever it's time to roll back a branch, we run an assertion saying that the state at that point is the same as the state before the rollback. So obviously this is not going to be true with most real processors today, but let's just use this as a motivating example for how we might get formal about the kind of guarantees we want. So how could we use this kind of thought experiment? We could just do a lot of testing with different test vectors and literally run this assertion at runtime. Or we could use something like bounded model checking to convince ourselves maybe for all sequences of programs of at most 5 instructions drawn from some simple vocabulary, this problem doesn't come up. Or we could use stronger formal methods to actually get a guarantee for any program running on the processor. This property is always true whenever we need to roll back speculation. So let me say a bit more about that last option. We know that in both the software and hardware development worlds, roughly speaking, there's a process where we think hard informally about the requirements of the artifacts that we're building, and then we implement them, and we iterate through various kinds of quality control measures like testing and code review. And eventually, through some fuzzy process, we become convinced, yeah, this is a good enough artifact, I'm going to send it out into the world. The problem with this iterative approach is it's never quite clear when you're done. There are words like coverage that get used, but it's hard to get rigorous guarantees that you've checked enough scenarios. So an alternative is formal proofs, where we can use a mathematical argument that establishes correctness of the system in any possible scenario, possibly even covering an infinite number of scenarios, though most real systems are fair to think of as finite objects. It's still a very large space of potential scenarios. And the version of this that I want to argue for, I'm going to summarize as mechanized end-to-end proofs of functional correctness. And I put in boldface 3 different constituents of this long phrase, and I'll explain each of them on one of the next few slides. So mechanized proofs, what am I talking about here? We're going to use an off-the-shelf theorem-proving software package called a proof assistant that is actually able to ingest the source code of your real system, and it's going to check formal arguments that talk directly about that source code. But we also need to write down our expectations of the system. We need to write down a specification, which will be source code in another language of logical formulas. And we need to write down a proof, which is going to be a step-by-step logical argument establishing that the system meets the specification. And then we run an algorithm that checks the proof's convincingness automatically, so we don't have to worry about fallible human auditors who might look at a conventional proof in a math paper. So how does that apply to the scenario I'm focusing on in this talk? Let's say there's some hot new vendor who comes out promising the most secure RISC-V implementation ever. And the customer wants to decide if it's a good idea to buy this product. Imagine the RISC-V Foundation maintains an official, formal specification of what it means to be a secure implementation of RISC-V. This is a piece of source code in a language of logical formulas. Then the vendor is required to produce a formal proof establishing that, say, this pile of RTL meets that specification. The client is skeptical, but he has his own installation of a proof checking program where he just pours all these ingredients into it and relies on that program to give the thumbs up or the thumbs down. The customer doesn't even need to read the RTL to get this assurance. He needs to trust the RISC-V Foundation came up with the right specification, but we hope it's a lot shorter than the RTL of the processor, so we're really better off than the traditional situation. Another point I'm arguing for is proofs of what's called functional correctness, which is easier to explain by saying what it's not. In the world of software, for instance, an example of not functional correctness is just proving this program will not crash, no segmentation faults. That's a good property to know, but it leaves out a lot. We could have some pretty serious bugs that wouldn't be caught by that proof. So instead we want to come up with a rather program-specific concept of correctness, like it gives the right answer. So in the world of computer architecture, that could mean we're going to prove that our fancy optimized out-of-order processor is observationally equivalent to an in-order processor, which serves as a simple reference design that says what the ISA is supposed to do. This notion of equivalence is a little tricky because when we're worried about Spectre kind of problems, we do need to think about timing as a first-class element. And it's expected that some of the timing is a lot faster in the out-of-order processor. That's why we put that optimization in there. But we still need to somehow capture that timing shouldn't be leaking our secrets. The last element of the approach that I was arguing for is doing end-to-end proofs. So we usually build systems with a series of layers that might span hardware and software components. And it's good to give each layer its own individual specification and do an individual proof about it. We might even have different engineering teams with very different backgrounds doing proofs about different parts of the system. That might be the only feasible way to get these proofs written. But then we should commit to plugging the theorems together to use them to prove a top-level specification for the whole system. And in that way, we'll catch any specification mistakes we made for the individual layers by making sure they actually work together properly. So in the example of some sort of SoC, we can imagine we have our optimized system on the left with an out-of-order processor, a cache-based memory system, highly optimized software code for some crypto routine. We'd like to show that behaves the same way as our spec. A simple reference processor, a naive memory with no caches, and a simple version of the crypto routine that's closer to what, say, some mathematicians wrote down originally, but it doesn't run as quickly. The challenge to get that end-to-end reasoning is to decompose this work, the formal validation work, in a modular way where we can analyze each component separately and not get caught up in the emergent complexity of all the pieces fitting together. So we want to basically rearrange it into a picture like this one. I want to focus in, show processor is good, memory system is good, crypto software is good, in a way such that if we do this analysis, we get a theorem for each of these, we can compose those theorems in a black box way to get the correctness of the overall system. So this is the basic kind of analysis that I'm going to be trying to make the case for here. We have some ongoing work showing lack of timing side channel vulnerabilities in combined hardware-software systems. It's a project at MIT done with a team including the people listed over there, one of whom, Murley, moved to Sci-5 since then. He's sitting right there, and you can ask him if you'd like to hear about some efforts of this kind in that setting. We built a library called Kami that works with a particular theorem-proving package, and I actually presented Kami at the RISC-V workshop a year ago, and it's also open source on GitHub. So how are we going to take that kind of approach and apply it to reasoning about avoiding information leaks through timing? There's actually a standard formal condition that's used to rule out bad information leaks, and it's called noninterference. So imagine we have, in general, some sort of system that has inputs flowing in on wires and outputs flowing out on some other wires. We're going to distinguish among the inputs which of those are secrets and which those are public. So the idea is It's perfectly fine for someone observing our system to learn the public inputs, but the attacker has won the game if he manages to figure out the secret inputs. And for simplicity here, I'll say all of our outputs will be public. So what does noninterference say? Imagine 2 runs of the same system like this, where we know the public inputs are exactly the same between the 2 runs, while the secret inputs might vary arbitrarily. It should still be the case that the public outputs are the same, no matter how we mess with the secret inputs. So to make this work as a description of timing security, we'll need to consider that inputs and outputs are not just values that pop in on the wires, but are basically time-stamped events. And we want to show that the timestamps on the outputs are not changing based on the timing of the inputs or the values of the inputs when those inputs have been marked as secret. So we want to do this, recall, in a modular way where we can analyze the processor, the cache system, and the software, each of these separately in a tractable local way, and then combine the analysis results to get our top-level theorem. So we apply sort of a uniform style of specification for each of those 3 key pieces, and I'll summarize it here. We have a system at some level of abstraction. I have little down arrows for inputs coming into the system, little up arrows for outputs, and the inputs and outputs and periods when nothing visible happens are arranged in a series of clock cycles. The timing is important. We don't want to allow the fact that something happens on a different clock cycle to leak information. So here's one run of some system like that. Imagine we now consider the thought experiment of changing the inputs. Let's imagine these are secret inputs to some other sequence of numbers. Then we should be able to rerun the system, get some other trace of all the inputs and outputs that happened and when they happened. And now we should try to convince ourselves we didn't leak any secret information through the way that the system execution changed. The way we'll do that is we'll apply an operation called censorship. It basically puts a big black bar across all the numbers that went into and out of the system. We'll assume that more traditional formal methods can check that there's no leak through the literal values going through the system. We only want to focus on timing. So I'll hide the values, just look at the up arrows, down arrows, and empty spaces in both the before and the after worlds. And I want to compare these, and the system is secure if in any such scenario, censorship leads to identical pictures before and after. When you forget the values and just keep the timing, it's the same even if you mucked with the secret inputs to the system. So we now want to take this picture and instantiate it for each of the key pieces of our hardware-software system. At the software level, we have a program that interacts with state through registers and memory. So now the trace of important events with timestamps is not just inputs and outputs, but also memory read and write operations. And I'm going to basically instantiate that picture up top with a slightly different censorship operation that hides the input and output values, and it hides the values written to and read from memory, but it keeps the memory addresses that we're touching. Why is that? Because we expect when you change the sequence of memory addresses you touch, you will get different timing because caches work that way. If you have better locality, then you'll get better time results for the execution of your code. And actually, this property is very well known in the world of cryptographic software implementation. It's called constant time code. You can basically assume that in any popular crypto library, the key routines have been written according to this guideline. So we formalized that for the theorem prover that we use so that we can prove that software actually does that. And then we need a similar property for the processor. It's basically the same picture as the software level, but when we prove the processor, we don't know what program runs on it. We prove that if you take any software code that follows the constant time property and load it on your processor, then the processor itself behaves in an analogous constant time kind of way. Meaning when you change secret inputs, the trace of memory addresses that are being touched is the same, and the memory accesses happen at the same clock cycles as they would have before you messed around with the secrets. And finally, we have to prove a property of the memory system, which doesn't have the top-level system inputs and outputs. It just sees memory read and write operations. And we have to show that when we forget about the values being written to and read from the memory, if we've changed the secret inputs to the program, then the trace of addresses is the same. So we'll, assuming that the cache structure ignores the values being written into the cache, only has timing dependent on the addresses, then we should be able to show that our memory system truly satisfies this property. So we've broken this down into formal conditions for each of these 3 key pieces: software, processor, memory system. We can prove them separately, and then we can mix and match, plug in a different processor, a different piece of software, whatever, if everyone commits to the same formal interface, then we can compose into whole system guarantees for any mix of components like that. So doing this for a new hardware design is a fair amount of work. You have to come up with formal invariants that relate the states between the optimized implementation and the simpler implementation that sets your baseline expectations of performance, and it takes some skills that are pretty specialized today to do this. But adding a new software program into this picture is relatively doable, because what we did was built a static analysis on RISC-V machine code that checks that it follows the rules of constant time coding as known to cryptography experts. And we proved once and for all that our static analysis is sound, meaning if it says good program, then that program actually follows the constant time coding guarantees. So this means with a new piece of software, you can just run this automatic analysis and get your theorem for free and plug that result into the larger formal analysis framework. We've also only applied this to pretty simple in-order processors so far, and we're working to try to show that the approach also scales to the out-of-order stuff. That is where things are really interesting for dealing with Spectre and meltdown kind of issues. Here's a slide with some code that's intentionally too small so you don't try to read it, but this is real C code implementing a popular cipher called Salsa 20 that's used in the wild for cryptographic operations. We compiled this with the RISC-V GCC, and our static analysis does accept this program, establishing that the machine code version of it truly does avoid dependence of memory access traces on the secret values that are being encrypted by this routine. So we can connect that with the rest of our results and get this processor with this machine code loaded on it is going to avoid timing side channel leaks. It's really important to emphasize that what I'm not selling here is a fix for the issues that Spectre and Meltdown brought up. Instead, this is an approach to validate purported fixes to those problems. I don't have any strong opinion about which kinds of fixes are going to become standard, but what we're trying to do is build a framework that's ready for them and can be used to show in a very rigorous way that they actually do give us security. As an example of another kind of approach, there's a project at MIT called Sanctum, which is led by Srini Devadas and involves a few students, including Ilya, who's sitting over there and will speak later in this room. And it gives you a secure enclave abstraction where you can have, say, multiple cores running code in a way where they're strongly isolated from each other, and that includes avoiding information leaks through timing. What we'd like to prove here, following similar style to what I was going through before, is that this system acts the same way as another one where each of these cores has actually been given its own cache, so that obviously there's no way to leak timing information through a shared cache. And with an appropriate notion of equivalence that treats time in the right way, we should be able to prove this theorem, establishing that the Sanctum implementation truly does provide the style of isolation that we're looking for. So I'll just finish up by thanking some of our funding sources, including the DARPA SITH program that's been mentioned a few times in the course of the summit so far, and also the National Science Foundation funds our multi-university project called the Science of Deep Specification, which is looking at the whole picture of modular correctness proofs of combined hardware and software systems, and involves educational aspects, like sometimes we run summer schools where people can come and get some training in using these kind of tools. And you can hit us on the web there at deepspec.org to learn more about the different parts of that project. All right, that's it. Thank you.